Hello everyone, welcome to this lecture series on thermodynamics. In this series of thermodynamic processes, we are going to discuss isothermal process and adiabatic process. We all know that a thermodynamic process is a chemical or physical process that takes place in a thermodynamic system which changes the system from an initial state to final state. That is, the system returns to its original state when all of its macroscopic physical properties resume their original values. There are different forms of thermodynamic processes. Among them, we are going to discuss isothermal and adiabatic process. First, let's see what is meant by an isothermal process. We have already studied that the thermodynamic processes are characterized by the thermodynamic variable that is kept constant. In the previous classes, we have seen that in an isobaric and isochoric process, in an isobaric process, pressure was the variable which was kept constant, and in an isochoric process, volume was the thermodynamic variable which was kept constant. Now let's see what is the variable which is kept constant in the case of an isothermal process. So an isothermal process is a thermodynamic process in which the temperature of the system remains constant. So simply we can say that in an isothermal process, T is equal to constant, or change in temperature is equal to 0, or dT is equal to 0. Here, in an isothermal process, the transfer of heat into the system or out of the system happens so slowly that the thermal equilibrium is always maintained. That means at a particular constant temperature, the change of a substance or object or system is known as an isothermal process. Now let's see some of the examples of isothermal processes. There are several examples. So first among them is the changes of state or phase changes of different liquids during melting and evaporation processes. Another best example is the industrial application of the Carnot's engine. We know that the working of a Carnot's engine can be well understood with the help of a cycle which is known as Carnot's cycle. So in this engine, some parts of this cycle, that is Carnot's cycle, are carried out isothermally. That is isothermal expansion process and isothermal compression process. Another best example is the working of a refrigerator. So a number of changes take place in the mechanism of refrigerator, but the temperature inside it remains always constant. Here, the heat energy is removed and transmitted to the surrounding environment. Another best example is the working of a heat pump. In the working of heat pump, the heat is either removed from the house and dumped outside, or the heat is brought inside the house from the outside to warm the house. That is, during summers, we require the room or the house to be air conditioned, while during winters, we require the room to be heated up. So either it will act as an air conditioner or it will act as room heater. In either case, the goal is to keep the house at desired temperature setting. So these are some of the examples of isothermal process. Now let's see how to calculate the work done during an isothermal expansion process. So in order to calculate the work done, let us consider an ideal gas which is taken in a cylindrical vessel fitted with a frictionless piston. Let us assume that this cylindrical vessel is placed on a source at a temperature T. This cylindrical vessel is made up of perfectly conducting walls and also the bottom. Now if the piston is slowly moved upwards, then the gas expands and it does some work. When the gas expands, there is change in volume dV. As the gas is expanding, this gas tends to cool, but it absorbs the required amount of heat from the source so that it keeps the temperature constant. As the temperature is remaining constant, we can say it to be an isothermal expansion process. Now, let us consider the piston is having a cross-sectional area A. This piston having cross-sectional area is moved through a small distance dx so that the gas expands by small amount of volume dV. As the expansion is small, the pressure of the gas practically remains constant, say P. Now we can calculate the force acting on the piston. Force is equal to pressure into area, F is equal to P into A. From this, we can calculate the small amount of work done by the gas. dW is represented by the small amount of work is represented by dW. dW is equal to force into distance moved, force into dx, F into dx. So dW is equal to, force is PA into dx. So dW is equal to, we know that A into dx is nothing but dV, change in volume. So dW can be written as P into dV. So this is the small amount of work done by a gas during isothermal expansion process. Now, this work done can be calculated by two different methods. One is graphical method and another is analytical method. Now let's see both the methods. One is graphical, another is analytical. So coming to the graphical method of calculating the work done during isothermal expansion. So in order to calculate this, let us represent the isothermal expansion process on a PV diagram. We know that pressure is taken on y-axis, volume is taken on x-axis. Here PQ represents, that is the isotherm PQ represents the isothermal expansion process. I is the initial state, F is the final state. PI represents the initial pressure, PF represents the final pressure. Similarly, VI represents the initial volume, VF represents the final volume. Here the volume is increasing from VI to VF. That means the gas is expanding. There is increase in volume, so we can confirm that it to be an expansion process. As the temperature is remaining constant, we can say that to be an isothermal expansion process. Now, let's calculate the work done in this process, graphical method. We know that the area under this isotherm is equal to the area under this isotherm is equal to the work done. So what is the area here? A, B, D, C. So area ABDC is equal to the work done, that is W, when the gas is expanding from a volume VI to a volume VF. So W is equal to area of ABDC. That is, the area occupied below the curve in between AB and CD gives the required value of work done. So this is the easiest way of calculating the work done, graphical method. Next, let's calculate the work done during isothermal expansion process by analytical method. So in this method, the work W can be calculated by integrating dW between the limits V1 to V2 as the volume is changing from V1 to V2. V1 is the initial volume, V2 represents the final volume. W is equal to integral 0 to W. This is the net work done. This is the small amount of work done. Work is changing from 0 to maximum work W. So integral 0 to W dW. That means integral V1 to V2 PdV, where dW is equal to PdV. We know that for a perfect gas, PV is equal to RT, ideal gas equation, or P is equal to RT by V. Substituting the value of P in this equation, we can write W is equal to integral V1 to V2. Instead of P, we can write RT by V dV. We know that the temperature is constant in an isothermal expansion process and R is the universal gas constant. So W is equal to RT integral V1 to V2 1 by V dV, or dV by V, RT log V over the limits V1 to V2, RT log V2 minus log V1, RT log V2 by V1 to the base E, or W is equal to 2.303 RT log V2 by V1 to the base 10. So this is the net amount of work done during an isothermal expansion process. On the other hand, if the gas is compressed, the work done on the gas, and is therefore negative. We know that work done by the gas is taken as positive, work done on the gas is taken as negative. So the work done for isothermal compression is given by W is equal to minus 2.303 RT log V2 by V1 to the base 10. Or it can also be written as W is equal to 2.303 RT log V1 by V2. So this is the work done during an isothermal expansion process. So we have discussed both the graphical method as well as the analytical method. Now let's come to the next thermodynamic process, that is adiabatic process. We know that an adiabatic process is defined as the thermodynamic process in which there is no exchange of heat from the system to its surroundings, neither during expansion nor during compression. That is, in an adiabatic process, Q is equal to 0. No exchange of heat. Heat is represented by Q. So Q is equal to 0. Now let's see some of the essential conditions for adiabatic process to take place. So the system must be perfectly insulated from the surroundings, thermally insulated from the surroundings, and the process must be carried out quickly so that there is sufficient amount of time for heat transfer to take place. So this is regarding the adiabatic process. Now let's have a look at some of the examples of adiabatic processes. One of the simplest examples would be the release of air from the pneumatic tire. The next example is the pendulum oscillating in a vertical plane is an example, and a quantum harmonic oscillator is also an example of adiabatic system. Now when we put the ice into the ice box, no heat goes out and heat comes in. Similarly, in the case of a flask where we will be using it for either drinking tea or coffee, it will remain hot for quite longer period because neither heat enters into the system nor outside the system. It is thermally insulated. These are the examples of the adiabatic process. Now, let's calculate the work done during an adiabatic expansion process. For this, let us consider a perfect gas which is enclosed in a perfectly non-conducting cylinder provided with non-conducting piston. That means the cylindrical vessel is completely thermally insulated from the surroundings. No heat can enter into the system nor come inside the system. Now, if the piston is moved slowly upwards, then the gas expands and does some work. Since no heat is supplied from outside the system or it is entering into the system, then also we are saying that work is done. In that case, we can say the energy required for expansion of the gas is taken from the gas itself so that its temperature falls. So in an adiabatic process, the temperature decreases. Now, let us assume that this piston is having a cross-sectional area A. When it is moved through a small distance dx such that the gas expands by small amount of volume dV, for a small expansion of the gas, the pressure P practically remains constant. Then the force acting on the piston is given by F is equal to P into A, force is equal to pressure into area, and small work done by the gas is equal to dW is equal to F into dx. So F is nothing but PA into dx, PdV, since dW is equal to PdV. So this is the work done during adiabatic expansion. Here also, we can calculate the work done during adiabatic expansion by two different methods. The first one is graphical method, second one is analytical method. Now let's see the graphical method of calculating the work done during adiabatic expansion. Of course, this case is different from the case of isothermal change in two respects. The first one is the container is made up of insulating material here and the curve is much sharper. Here also, in order to calculate the work done during adiabatic expansion, let us represent the adiabatic expansion process on a PV diagram. Here, pressure is taken on y-axis, volume is taken on x-axis. I represents the initial state, correspondingly Pi represents the initial pressure, Pf represents the final pressure, F is the final state. Vi represents the initial volume, Vf represents the final one. Now we can calculate the work done graphically. So the area under this curve PQ represents the work done. So area ABDC gives the work done. So work done in adiabatic expansion is given by the expression W is equal to area ABDC. Thus, the area occupied below the curve in between AB and CD gives the required value of work done. Now let's see the next method of calculating the work done during adiabatic expansion, that is the analytical method. So analytically, work done can be calculated by integrating between the limits V1 to V2, where V1 and V2 represents the initial and final volumes. So W is equal to integral 0 to W dW integral V1 to V2 PdV. We know that in the case of an adiabatic change or adiabatic changes are represented by the equation PV to the power of gamma is equal to constant, or P is equal to K by V to the power of gamma. Substituting this in this equation, we will get W is equal to integral V1 to V2. Instead of P, we will write K by V to the power of gamma dV, or K is a constant. Integrating it over the limits V1 to V2, 1 by V to the power of gamma, that is V to the power of minus gamma dV. On simplifying, we will get W is equal to K by 1 minus gamma, applying the limits V2 to the power of 1 minus gamma minus V1 to the power of 1 minus gamma. We know that here PV is equal to PV to the power of gamma is equal to constant. That implies P1 V1 to the power of gamma is equal to constant, P2 V2 to the power of gamma is equal to constant. Now substituting this in this equation, W is equal to 1 by 1 minus gamma, K keeping it inside. Instead of K, we can write P2 V2 to the power of gamma and V2 to the power of 1 minus gamma minus P1 V1 to the power of gamma into V1 to the power of 1 minus gamma. On simplification, we will get W is equal to 1 by 1 minus gamma P2 V2 minus P1 V1. Now, if T1 and T2 are the initial and final temperatures of the gas, according to the gas equation, P1 V1 is equal to RT1 and P2 V2 is equal to RT2. Substituting, we get W is equal to R by gamma minus 1 into T1 minus T2. So this is the expression for the work done during an adiabatic expansion. W is equal to R by gamma minus 1 into T1 minus T2. Here, R is a constant and gamma is also constant. Now, in this, the work done during an adiabatic expansion, since these two are constant, we can say that this work is proportional to the fall in temperature. So this is the adiabatic expansion process and the method of calculating the work done in an adiabatic expansion process analytically. On the other hand, if the gas is compressed, what happens? The work is done on the gas. When the work is done on the gas, it is negative. The work done for adiabatic compression is given by W is equal to minus R by gamma minus 1 into T1 minus T2. So we have studied how to calculate the work done both graphically and analytically. Now let's study the differences between isothermal and adiabatic processes. So coming to the isothermal process, it is a process or isothermal process is defined as one of the thermodynamic process which occurs at constant temperature. Adiabatic process is defined as one of the thermodynamic process which occurs without any heat transfer between the system and surroundings. The isothermal changes are represented by the equation PV is equal to RT. The adiabatic changes are given by the equation PV to the power of gamma is equal to constant. Here, in the case of isothermal process, internal energy remains constant. In an adiabatic process, internal energy changes. In an isothermal process, there is transfer of heat. That is, in order to maintain the temperature, heat can be added or released to the system. Q can be added or released to the system. Here there is no transfer of heat. No need to add or release the heat. No, there is no constant temperature maintenance here. In the work done in an isothermal process is given by the expression W is equal to 2.303 or T log V2 by V1 to the base 10. The work done by adiabatic process is given by the expression W is equal to R by gamma minus 1 into T1 minus T2. The work done in an isothermal process mainly depends upon the initial and final volumes of the gas. Here, the work done in the adiabatic process mainly depends upon the initial and final temperatures of the gas. It's a relatively slow process. It's relatively a quick process. So we have just seen the differences between isothermal and adiabatic process. Hope you understood what are isothermal processes, what are isothermal and adiabatic processes, examples of isothermal and adiabatic process, and how to calculate the work done in isothermal and adiabatic process, both by graphical method and analytical method. We have also come across the differences between the isothermal and adiabatic process.